Given functions f of x equals ln x over x, g of x is cosine pi over 3x, and h of x, we're going to look at some interesting limits to really push our understanding. The key to all of this is really to think, okay? There's no quick tricks or anything. You have to think it through layer by layer. Now, h of x is shown below, pretty straightforward. G of x is here, pretty straightforward. This we need to think about. So we have absolute value of ln x over ln x. Absolute value of any function over itself should generally just produce either 1 or -1, because anything divided by itself is 1. The absolute value part is guaranteeing that the numerator is always positive, and then the denominator could be either positive or negative. So we want to think about the function ln x, and it's positive everywhere greater than 1. It is negative everywhere less than 1. And so this function here will be positive when it's greater than 1, negative less than 1, undefined at 1, because we'll have division by 0. So just a little sketch of ln x over x, or absolute value of ln x over x. We should see a graph right here. It's either 1 or -1. When x is greater than 1, the function is 1. And when x is between 1 and 0, not inclusive, the function is -1. So we're able to break down what this function does, and we want to be able to think about that for any of these functions with absolute value of something over itself. It's always 1 or -1. It's just a question of when. Okay, so now we're going to start with the limit as x approaches 1 from the left of f of x. And so now that I've got this graph of f of x sketched here, this is not too bad. Approaching 1 from the left, well, we can see that we are -1. Approaching 1 from the right, as our inputs approach this 1 from the right, we can see that our outputs are +1. Now, limit as x approaches 1 of f of x does not exist, because the left limit does not agree with the right limit. The limit of x approaches 1 from the left of f of x is not the same as the limit as x approaches 1 from the right of f of x. But here's where it gets kind of interesting. If we compose this limit as x approaches 1 of g of f of x, even though the limit of x approaches 1 of f of x doesn't exist because it doesn't agree, we're going to see something interesting happen. So this is where we think. We think about as x gets really close to 1, first it goes through f of x. And as it's going through f of x, as it gets close to 1 from above, so as x is getting like close, we'll call it like 1.001, then we're getting close to +1. As x gets close to 1 from below, say like 0.0999 as our inputs, x is, well, it's -1 the whole time, but you can say it's getting close to -1, which I wrote -1. Okay, so as x is getting close to 1, f of x is getting close to two different things, positive and -1. However, as we put those into the g function, as we get really close to +1, so from above, we're coming at +1 from this, right? And our output is getting really close to 2. It is just 2, it's constant. As we get really close to 1 from the left, we get really close to 1 from below, we're just -1. And our output, as we get really close to -1, is, well, 2. So that's it. And so we have the same output, even though it came from two different places, +1 and -1, right? 1 and -1, those two things we're approaching from f that made it does not exist together go to the same thing, and so suddenly we exist, and the limit is 2. So through composition, a limit that goes to two different things can eventually resolve itself out to going to one thing, which is maybe not that intuitive. Let's look at some more examples. Limit as x approaches 1 from the left of f of x times h of x. Okay, so as x approaches 1 from the left. So we have to interpret this as gets close to 1 from below, meaning we want to think about like 0.999, whatever. But we're getting closer to 1 from less than 1. And so as far as f of x concerned, getting close to 1 from less than 1, here's our input of 1, it's down here at negative 1. So this part of it is going to be negative 1. Now we're going to look at what's happening to h of x as we get close to 1 from below. And getting close to 1 from below, well, we're just 2 the whole time. So we get to say h of x is 2, or the limit is 2. And so now it's negative 1 times 2, and that is negative 2. The limit as x approaches 2 from the left of f of g of h of x. So we're basically saying as x gets close to 2 from below. So you can imagine it as being 1.999, whatever, right? But those are the inputs. As we get closer and closer and closer to 2 from lower inputs, what's happening? So first we look at the function h. Our input of 2 from below, if we approach it from 1.99 whatever and 1.99 even closer and even closer, we're getting really close to the output of 2 up here. So the left side of the limit's getting close to positive 2. So this is getting really close to 2. As that gets really close to 2, g is now accepting inputs that are really, really close to 2. And by really, really close to 2, this is a constant function, so it just literally is 2 the whole time, I should clarify. So we're taking g of 2 this whole time. And here's cosine of pi over 3x. So cosine of 2 times pi over 3. And that limit is pretty straightforward. We're coming from exactly 2 that whole time, so we're doing exactly cosine of 2 pi over 3 the whole time. Cosine of 2 pi over 3 is negative 1/2. Okay, and now there's no like approaching from above or below. We're just literally that the whole time. And so here's negative 1/2, and we put it into the f function. So we look at our f function, negative 1/2. That's not so useful because there is no negative 1/2 hanging out in our f function. So we would say that this limit does not exist. Okay. There is no place where the negative 1/2 is defined. In our next example, we're going to look at limit as x approaches 0 of f of 1 over g of x. So x approaches 0. That means we have to consider limit as x approaches 0 from below or from the left, and limit as x approaches 0 from above. And it starts with this g of x. So we're going to look at the function g of x. G of x is cosine of pi over 3x. So cosine pi over 3x. As we get really close to cosine of 0, and our cosine function generally looks like this. It's a little modified because of this pi over 3, but it still has this behavior around the input of 0. As we get really close to inputting 0, our outputs, regardless of which way we're coming at it from, are getting really close to 1. And it's close to 1, but it's always slightly less than 1. Right? It's important that we're coming from below because, okay, here we have f of 1 over, and we're getting really close to 1, but slightly less than 1. So less than 1, but really close. So perhaps we imagine that this is f of 1 over 0.999, whatever. So that's going to be, the inside here is going to be really close to 1. It is going to be slightly larger than 1 because division by a smaller number creates a bigger number. So here, or sorry, divided by small creates big, generally speaking, when we talk fractions. So this is slightly more than 1, this whole thing here. as we approach, we get slightly more than 1. So now we're taking f of slightly more than 1 as we sort of consider how the limit behaves. And so let's look for our f function. We can look at our input of 1 here, and we're taking f of slightly more than 1 as this limit comes in. And as we do that, that means we're coming from above 1. And when we're coming from above 1, our output is positive 1. So the answer here is positive 1. Limit as x approaches negative 2 of f of h of x. So limit as x approaches negative 2. We want negative 2 from below, which in this case, right, that left-sided limit is going to be like negative 2 point, like a little bit more in terms of magnitude than negative 2. And from above, from the right, is going to be like negative 1.9999, whatever. And so that is what we have to consider. So we're going to look at our x, limit as x gets to negative 2 from both directions of h of x. Okay. From this side, we are approaching negative 2, and our outputs approach 2. Our other limit agrees. Our outputs are not necessarily approaching 2, they just are 2 the whole time, but they're also approaching 2. So from this part of it, we just are 2 the whole time. Here we get close to 2 from below. Right? Our outputs get close to 2 from below as our inputs get close to negative 2. Now if we put that into the f function, getting close to 2 from below, so like 1.99, so let's say this is 2, and we approach it 1.99, etc. Well, we're just 1 the whole time, and if we just straight up R2, well, we're also 1 the whole time. So this all comes out to be 1. Let's look at these limits on the back. Okay. Limit as x goes to infinity of this function here. Now, exponential growth is much, much faster than polynomial growth. So we can basically ignore the polynomial terms here, and we just focus on the dominant terms, 2e to the x over e to the x. Now, 2e to the x over e to the x, we know that e to the x and e to the x will cancel. We just take a quick moment to make sure that we account for positives and negatives. E to the infinity, as we put in infinite positive values to e, we're getting out bigger and bigger positive values. So this whole thing will be positive, and so we just get an answer of 2. The key thing here is that we don't consider the non-dominant terms when we push our limits out to infinity, because comparatively, they get less and less and less and less influential, and this basically grows in a ratio of 2e to the x over e to the x, which is a ratio of 2, the bigger and bigger you get. If we push out to infinity of this function, here we have 7x plus ln x, so the dominant term in the numerator is 2x. We have 2x minus 5e to the negative x. We might be tempted to think this is the dominant term because it's exponential. However, if we imagine putting in bigger and bigger values here, e to the negative very big number actually gets really small. Okay, so small, in fact, that this part approaches 0. So even though the e to the x is the quote-unquote dominant term, because it's getting really, really small, it sort of deletes itself, leaving us with a dominant term of 2x. And so we get 7x over 2x, because by comparison, 7x is going to grow way, 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 way bigger than ln x. And so this limit will be the same thing as the limit as x goes to infinity of 7x over 2x. The values will never be identical, but the limit will approach the same thing over time. And we pay attention to the positive infinity, so this is positive, positive. So when we cancel the x's, it is logical to say that we are 7/2. What does this mean? Again, if we look at this function, as we put in bigger and bigger and bigger and bigger and bigger values, over time, this becomes irrelevant compared to this. This pushes itself to 0, becoming irrelevant. This gets really big too, and it's that ratio of 7x to 2x over time that comes out to dominate and be what the limit approaches. All right, we have limit as x approaches 1 from the right here. So that means, right, we're picking values slightly bigger than 1, so like 1.0001 or whatever, and we're getting closer and closer to 1 from that direction. Let's look at the structure. Here we have x minus 1 over the absolute value of x minus 1. We know that this function piece itself is always 1, but it can be positive or negative 1. It is positive when we put in x's greater than 1, and it is negative when we put in x's less than 1. Okay? So that's what that's going to do. We are taking a limit as we approach 1 from the positive side, or values that are slightly bigger than 1. So if we are putting in values slightly bigger than 1, when we do subtract 1, we'll get slightly more than 1 positive left over. So all this part here is doing is acting as positive 1. Okay, so this all is just positive 1. Which means the only part to really consider now is this. So we can say this is an equivalent limit, is the limit as x approaches 1 from above, or from the right, of 2 to the 1 over x minus 1. Okay, now this we can figure out with direct substitution. We can't, well, not direct substitution. We can't literally plug in 1 because we get 1 divided by 0. But we can plug in values that are just slightly bigger than 1. So we can imagine plugging in this. And what we'll have here is 2 to the 1 over just more than nothing, okay? And 1 divided by really small is going to result, this whole thing is going to get really, really, really big. So we're raising 2 to a massive power, essentially 2 to an infinitely large power, and so this limit is going to grow without bound. So our answer here is going to be does not exist, and we are heading off to positive infinity. So the absolute value part here, the x minus 1 over x minus 1, helped us know that it was a positive thing that we'd approach, and then we can consider what's happening here as we plug in values of 1 from the right. If this had been 1 from the left, we would probably get a little bit of a different story. So you can consider that as well. Oh, actually, I figured that that would be a good thing to look at. So here we go. 1 from the left, x minus 1 over the absolute value of x minus 1. It just makes us either positive 1 or negative 1. As we approach 1 from the left, now we're plugging in like 0.99, whatever. Okay, so this is going to be slightly less than 0, which means this is going to, or sorry, yeah, slightly less than 0, which means it's going to be negative. And this is going to be positive, but also slightly less than 0, or slightly more than 0, I guess. But the point is negative over positive, that will be essentially negative 1. So this is equivalent to the limit as x approaches 1 from the left of negative 1 times 2 over 1 to the x minus 1. Now, if we consider what happens when we put in numbers slightly less than 1 here, we're going to get negative 1 times 2 to the 1 over. If I put this in, that minus 1, I'm going to get like negative 0.0001. Okay, so now what's happening? We have 1 divided by small, and it's going to get really, really big. But it's divided by a negative small, and so it's going to get really, really big, negative big. And so we're getting negative 1 basically to 2 to really, really, really big values that are negative. Well, here's the deal. 2 to a negative power is like division by 2, or 1 over 2. I'll write it like this, to a really big power. And this is going to approach 0. So this whole limit is going to approach 0. This negative 1 doesn't matter because as we're approaching 0 from the negative side, sure, but 0 is 0. There's no positive negative 0. All right, next we have limit as x approaches negative infinity of this sine of all this stuff going on inside. Okay, so as we go to negative infinity, let's just think about it inside out. We raise negative infinity, so a negative really big number here. This becomes basically a really infinitely large number. Adding 1 doesn't do a whole lot here. So we're taking sine of ln of a massive number all over some massive negative number squared, but that's going to just turn it back to positive. Okay, comparatively, this, something squared, compared to ln of something, the denominator is going to grow way, 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 way bigger. This is big, and this is big. And so big over big in the scale of infinity, this whole thing's going to get closer and closer and closer to 0. Okay, so we're taking essentially sine of 0, and to take sine of 0 is basically 0. Sine, yeah. And so this whole limit is equal to 0. Now, it's probably smart to think about, are we approaching big over big from the positive side or the negative side? It's coming from the positive side, and as far as sine is concerned, that doesn't really matter. Sine is continuous. All right, last one here. We have limit as x goes to infinity of arctan of all this good stuff. This we can treat in a number of different ways, but I'm going to just do imagining what's happening. So here we have e to the square root x over e to the x. And I'm putting in infinity to represent putting in bigger and bigger and bigger and bigger and bigger numbers. And it's pretty logical that if you raise e to a supermassive number compared to e to a supermassive number, but you're square rooting it, this is going to get way bigger, even though the numerator is getting massive also. And so if we divide by way bigger, well, we're heading to 0. E to the x is always positive. E to the root x is always positive. So we're getting way bigger, going to 0. We're coming at it from the positive direction in case that matters. So we're essentially taking arctan of 0. If we imagine our arctan functions, quick curve, okay? It doesn't actually matter if we're coming at it from above or below, because arctan of 0, either direction, is going to approach 0. In this case, we'll be approaching it from the positive direction because this all comes out positive. We're approaching 0 from positive, so like 0.0001. So we're actually coming at it from this way, not the other way. But it doesn't matter because we're approaching the same thing. So arctan of 0 is 0, so this whole limit is equal to 0. Okay, so that's sort of how you can think about these really complex ones. There's layers to it, but as we said before, the key is to think. Break it down, think about the approaching from above, approaching from below, layering it through, and all those different pieces are really important.